All right, before we get into gas laws, I wanted to quickly recap the solid, liquid, and gas states. In fact, this is covered in 3 different sections in your book, but we'll do it pretty quickly because I'm assuming most of us are familiar with solids, liquids, and gases. But here's a good image from our book. It kind of outlines how particles behave when they're in the solid state, liquid state, and gas state. So in a solid state, you can tell that the particles are held close together and they are held in fixed positions, meaning they don't even need a container. In fact, when I was looking at this, I was even wondering, heck, if this is a solid, how did they get it in through this hole? But that's neither here nor there. Anyways, if we look at liquids, they behave a little bit differently. As you can tell, a liquid fills the bottom of the container. Things are still held close together, but it's no longer in a fixed position like a solid state. And then in the gaseous state, the particles are really far apart and completely fill their container. So if we think about the forces here, these two have cohesive forces. Right? Because if we look at these, we could say, well, they're being held together, right? So that's one of the key terms you see here. They're close together and close together here, so that the cohesive forces are causing them to stick together. If we look at other forces, though, in the gas state, we could say, well, the gas state actually is being dominated by disruptive forces. Meaning these particles are flying around so fast that they're no longer going to be close together, but rather they're going to be far apart. And if you remember, disruptive forces are due to kinetic energy. Those particles have so much kinetic energy, they're just going to fling around in the container and fill the entire thing up. Where cohesive forces, on the other hand, are due to potential energy. And potential energy, we said, is the attractive force between different particles. So in this case, they have attractive forces between all these particles, holding them close together. So that's one of the main differences here is solids and liquids are dominated by cohesive forces. With that in mind, there's weaker cohesive forces in the liquid state than solid state, but still dominated by cohesive forces. Whereas in the gaseous state, things have so much kinetic energy that they're basically being ejected apart from one another, and disruptive forces are dominating. All right, so let's go ahead and make just kind of a brief list. And in this list, we'll just start out with solids. And I apologize if this is kind of elementary, but solids have high density compared to liquids or gases. And like I said, this is a general rule. We saw an example in a previous video where a solid iron actually had a lower density than a liquid like mercury, but for the most part, this holds true. And they have definite shapes, meaning doesn't matter what the container is, it's got a defined shape, right? And then we also said that it has small compressibility. And it's got small thermal expansion. So these are all characteristics, but like I said, these are general guidelines. They're not absolutely true. There are some solids where you can compress them more than others, and there are some solids that have really low density. It just depends. And then liquids would be next. Liquids typically still have a high density because they're dominated by those cohesive forces, so things are going to be held together, but they typically have lower density than solids. But again, there's exceptions. If you think about ice is water and it has a lower density than the liquid. So there's always exceptions in science. I know it's something that drives students nuts. And then it's got an indefinite shape. And the way most people will remember this is it fills the bottom of a container. All right, so liquids always fill the bottom of containers. They have small compressibility. And it also has small thermal expansion. Okay, And then last but not least, let's go into gases. Gases typically have a lower density than liquids or solids because now they're being dominated by disruptive forces. They have an indefinite shape. I'm just going to abbreviate that. And they fill an entire container. And they have a large compressibility. And then they also have a moderate thermal expansion. I know one thing that always bugged me when I was a kid was I remember playing with super soakers. I was definitely a 90s kid. And I always thought that, hey, with the super soaker, when you squeeze that handle and you kind of pump it, I thought you were actually squeezing the water, which is what made it squirt out. And then I found out later that it actually is the gas within your super soaker that's being squeezed, and that's what's ejecting out the water because water has really small compressibility. In fact, if you ever want to try an experiment at home, try filling up a super soaker absolutely full, pump it a bunch, see how far you can squirt it, and then test it when it's half full, meaning half air, half water. You'll see when it's half air, half water, you actually get way better super soaker spraying ability. So it's kind of interesting. And then the last thing I wanted to talk about really quickly was how it fills the container when you've got a gas. And this is something that's kind of hard to imagine because most gases are colorless. But here's a situation, right? So over here, you can see that it's closed. We've got a valve between these two containers. And over on this side, we've got a colored gas. In fact, it kind of looks like bromine vapor to me. And what we're going to, or maybe it's iodine, I'm not sure. But either way, when you open that valve, you'll end up filling this entire container. You don't need to do anything to allow this to happen. It's just nature doing nature's thing. And in fact, that property is called diffusion. And diffusion basically says if you spray perfume in one portion of your house, over time, those particles will slowly diffuse all the way over to another side of your house. It's just going to occur naturally. And that gets behind the idea of gases filling their entire container. If you give them enough time, you'll essentially form an equilibrium where the gas will distribute evenly among all the open space. All right, I hope that makes sense, but let me know if you have any questions.